Alright, so today we're going to look at non-real roots. So we're going to start with this polynomial g of x. Notice it's in factored form, but notice that if we were going to multiply it out, this would be a third degree polynomial, right? There's my degree, remember that? And the leading coefficient is positive. So we already have an idea that it's going to look something like that. But what we want to do is we want to find the zeros. We want to know what happens in this middle part. We want to know where our x-intercepts are, our zeros, our roots, right? And so if our polynomial is equal to 0, then that means one of our factors is 0. So either x plus 2 is equal to 0, in which case x is equal to negative 2, or x squared minus 7 is equal to 0. So now in this case we're going to solve for x. We're going to add 7 on both sides. I'm going to leave a little space here on purpose. I'm going to push my 7 over like this. Because now to get this x by itself, I'm going to take the square root of both sides. And when I take the square root, I have to put plus or minus. So a square and a square root undo each other. And x is equal to plus or minus the square root of 7. So I have 3 roots. But my roots are different types of numbers. X equals negative 2. This is a real, rational root. Rational means it can be written as a ratio, as a fraction. But the square root of 7, or negative square root of 7, it is a real number, but it is irrational. So I want you to take your calculator and I want you to type in square root of 7. Our calculator spits out this decimal answer, but this is not the complete answer to square root of 7. This is just as many places as the calculator goes to. This is actually a non-terminating decimal. It never stops. There's also no repeating pattern to it. So that is what makes the square root of 7 an irrational number. It cannot be written as a ratio. We cannot take this decimal and turn it into a fraction because it never stops. So we don't even know where to stop writing it. But it is a real number, which means we could graph it on the number line. It is approximately plus or minus 2.6. So if I was going to graph my roots for this polynomial, I would be able to do that. I would go to negative 2, and I know that negative 2, 0 is a point on my graph because negative 2 is a root. And then I know that the square root, negative square root of 7 is in between negative 2 and negative 3, a little bit closer to negative 3. So that's an x-intercept. And then I know that positive 2.6 is also an x-intercept. So I know between positive 2 and positive 3, a little bit closer to the 3, there's an x-intercept. So let's go to y equals on our calculator. and clear out whatever's there from the other class. And let's type this in factored form, parentheses x plus 2, and then parentheses x squared minus 7. And let's graph that. Now your window might be changed like mine from last period, so I'm going to go to zoom. I'm going to go down to standard so that I can see things a little bit better. So, can you see the x-intercept at negative 2? And then there's the one at negative square root of 7. And then there's the one at positive square root of 7. Right? So we can kind of tell that our graph just goes barely up like this. And this one goes way down. Then it comes back up. So, follows the pattern of n behavior that we would expect from a cubic function, but it kind of goes way down in the middle. All right, so you remember the other place we can find our zeros is on our table. If I go to my table, and I have my table set to count by tenths. If you don't know how to change your table set, that's on top of window, second table set. So I can count start my table on 1 and I can count by 1. That's what our table usually looks like. And I see at negative 2, when x is negative 2, the output is in fact 0. That's great. And I said, well, let me find my other zeros. Let me just look on my table. Can you find them? They're not going to show up because they're irrational. So even if I go to table set, and I'm going to ask my table to start at negative 3, and I'm going to have it count by 0.1. You're still not going to find a 0. Because the irrational number is not going to show up on your table. But you do get a little bit of information. So I want you to look right between the negative 2.7 and the negative 2.6. Do you see how at negative 2.7 our output is negative? And at negative 2.6 our output becomes positive. So think about this. If your output is negative on negative 2.7, and then when you get to negative 2.6, your output is positive, but if your curve is continuous, that must mean that between negative 2.7 and negative 2.6, somewhere you're going to have to cross the 0, right? So your table can tell you, hey, somewhere between negative 2.7 and negative 2.6, there's an x-intercept. But you're only going to know it's the square root of 7 algebraically. You're not going to be able to find that answer exactly in the table. All right, let's go to 2.6. Scroll down quite a bit. Scroll down a lot, actually. All right, you see at 2.6 I have a negative answer, and at 2.7 it switches to a positive answer. So what's happening on my graph? At 2.6 I had a negative answer, but over here at 2.7 I had a positive answer. So somewhere in the middle I must have hit 0. It's all about the roots, the x-intercepts. All right. Now we're going to do h of x. I'm going to change one thing about this problem. See if you can figure out what I changed. H of x equals x plus 2 times x squared plus 7. What's different between g of x and h of x? Plus 7 instead of minus 7. It's probably not a big deal, right? Is it still a third degree polynomial? Sure. Does it still have positive 1 for the leading coefficient? Sure. So should it still have basically this shape of n behavior? Alright, but now let's find out a little bit more about it. Well, our first factor is the same, so we have a 0 at -2. Now, I can set my second factor equal to 0. X squared plus 7 equals 0. And then I'll subtract 7 from both sides. And then I'll take the square root of both sides, putting a plus or minus in there. So now x is going to equal plus or minus the square root of -7. Alright, let's go back to our calculators. Home screen. Sorry, I turned it off. And let's press square root of -7. What did our calculator tell us? Error, a non-real answer. Alright, our calculator told us error last semester too. You remember it mainly told us error when we were trying to divide by 0? That's because division by 0 is undefined. This is not the same kind of error. So notice what it says after error. In fact, let's write down what it says in our notes. It says error, but it says non-real answer. So you did not type anything wrong. You did not commit a mistake. That's not what that error message means. Our calculator only operates in the real number system, and this is not a real number. Okay? So what is it if it's not a real number? It's an imaginary number. So if you remember from Algebra 2, imaginary numbers, you'll know you're working with imaginary numbers because there will be this I symbol. And it's written as kind of a italicized or script letter I. And that is equal to the square root of -1. So I is not a variable that is changing its value on different problems. I is a number. It's an imaginary number, and it always equals the square root of -1. So if I have x equals plus or minus the square root of -7, I would handle that simplification by saying, well, that's plus or minus the square root of 7 times the square root of -1. So the square root of 7 is just the square root of 7. I can't simplify that any further. The square root of -1 is I. So these are my other two roots. So I still have a total of 3 roots, right? I have x equals -2. That's a real root. But I have x equals positive square root of 7i and x equals negative square root of 7i. And these are not real numbers. They're imaginary numbers. So look at what happens when we graph it. If you go to your y equals, And all I really have to do is come in here and change this minus sign to a plus sign. And then I graph it. Well, I see that, and I'm like, wait a minute, I know it's supposed to do this end behavior. So I'm going to go to my window, and instead of only going to tens, I'm going to put everything to 30. So negative 30 to positive 30. And then on my y's, negative 30 to positive 30. And now I'm going to graph it. Alright, does that have the end behavior that we would expect? But how many times is it touching the x-axis? Just that one time at x equals negative 2. So these are zeros. They are roots. In other words, if I take this number and I plug it in here and I square this and multiply this, it will come out to 0. So they're a 0, but they're not going to show up on the graph as an x-intercept because they're not real numbers. So that's a significant departure from everything we've been studying so far. Does that make sense? Alright, so let's do another one. We'll call this one f of x. And we're going to have, in factored form, x plus 3 times x squared minus 4x plus 7. Looking for roots, zeros. Well, I hope you can find one right away. What's our first root that we know? Negative 3. That's a real rational root. We can plot it. It's going to be an x-intercept. That's lovely. Alright, now we have this. When I spy this quadratic, the first thing I think of is, can I try and factor it? Well, if I go x, and I have to get a 7, but my middle term is negative, so I'd have to have two negatives. But the only thing that makes 7 is 1 times 7. But then that's going to make negative 8, not negative 4. So it just does not work to factor. Alright, well, let me set it equal to 0 like I did on that other problem. So remember, our strategy was set it equal to 0 and then got the x by itself. Do you see the problem with that? I have an x here and I have an x here. I'm not going to be able to get the x by itself, am I? It would appear that we're stuck. So we're going to have to use something called the quadratic formula. The first thing we have to know about the quadratic formula is the conditions under which it is applied. So the quadratic formula is applied to an equation that goes ax squared plus bx plus c equals 0. You have to be working with this equation format in order to use the quadratic formula. If you're not equal to 0, you have to add or subtract and get it equal to 0. And then the quadratic formula says this: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I apologize for not being able to sing well, but it's to the tune of Pop Goes the Weasel, and that's your quadratic formula. And it's long, but it's not hard. It's a matter of substituting in values. Do you remember it from last year? You can nod up and down. You're like, yeah, I know how to do this. Alright, so we're going to do the quadratic formula to this equation. My suggestion is that you always start by writing down what A, B, and C equal. So A is your number that's multiplied by x squared, which is 1. B is your number multiplied by x, which in this case is a negative 4. And then C is your constant term, which is a positive 7. Once you've identified A, B, and C, it's a matter of just plugging them into the equation. So it's going to be the opposite of negative 4 plus or minus the square root. Negative 4 has to get squared. You want that in parentheses when you square a negative. Minus 4 times 1 times 7. And then all over 2 times 1. Now, if you type that all in the calculator at the same time, you're going to get a decimal answer. We don't want our answer in decimal form. So we're just going to work under the radical. We're going to simplify some other stuff. So the opposite of a negative 4 is going to be 4. Now, this stuff that's under the radical, you can either do in your head or you could type that into the calculator. So you're going to have 16 minus 28, which is going to give you negative 12. But if you have larger numbers, you can always just type what's under the radical in the calculator. And then 2 times 1 is 2. Alright, so now we have to simplify. So I'm going to write this as 4 plus or minus. Now I'm going to simplify my square root of negative 12. There's a perfect factor of negative 12, which is 4 times 3 times negative 1. I'm going to put the negative 1 at the back on purpose, and then over 2. So now that's going to be 4 plus or minus. Now, what is the square root of 4? 2. Then the square root of 3 is the square root of 3. And then what's the square root of negative 1? I. And then divided by 2. So actually, I had said if you typed it in the calculator, it would give you a decimal. Actually, in this case, if you typed it on the calculator, it would tell you error, non-real answer, because this came out imaginary. So now we can simplify one bit more, which I can divide each term by 2. So 4 divided by 2 is 2. This is all one term. So if I take 2 square roots of 3i and divide it by 2, that would be 1 square root of 3 of I. So I'm just going to write square root of 3i. So my polynomial has 3 roots. It has a real rational root of negative 3. I'll be able to see that on the graph. And then these 2 roots are in the imaginary. They have an imaginary component. So we call these complex numbers. And our complex number is always written A plus BI. Real number part plus imaginary part. So we have 2 plus the square root of 3i. And 2 minus the square root of 3i. Those are your other 2 roots, but you're not going to see them on the graph. Alright, one more thing before we take a short break. And that is powers of I. This is kind of cool, I think. If you like patterns, you'll like this. powers of I. Alright, so we're going to start with just I, which would be I to the first power, and that is equal to the square root of -1, but I'm just going to say that's just I, right? I to the first power is I. Well, what if I take this equation here and I square both sides? I squared would be the square root of -1 squared. So what happens if you take the square root of something and then you square it? Those are inverse operations. So how much is I squared? I squared is just -1. So what if I have I cubed? Well, I can think of I cubed as being I squared times another I. Wouldn't that make I cubed? But now I know that I squared is -1. So -1 times I would be -I. Well, what if I had I to the 4th power? There's a couple ways I could think about that, but I think of it like I squared times I squared. That makes I to the 4th power. But I squared is -1. So what happens if you do -1 times -1? +1. Well, what if I do I to the 5th power? I can break I to the 5th power down to be I to the 4th power times I. Right? You remember your rules of exponents? We just add one more I here. But I to the 4th is 1, and 1 times I is I. Well, what if I do I to the 6th power? Isn't that I to the 4th power times I squared? So I to the 4th power is 1, and I squared is -1, so that's going to be -1. Do you see this pattern? Right? Got I, -1, -I, +1. Then what do I have? I, -1. What's going to come next? -I, and then +1. And it's going to keep going in cycles of 4. Right? Do you see why that's happening in cycles of 4? Because anytime I have an exponent, I can break it down into parts. And my I to the 4th is always going to come out to be 1. So that means you can calculate something like I to the 33rd power. So here's the way I think about it. I take the number 33 and I divide it by 4. 33 divided by 4 goes in 8 times with a remainder of 1. That means I would cycle through this pattern 8 whole times, and then I'd have 1 left. So that's I to the 1st power. So I to the 33rd power equals I, because that's the first one. But what if I had I to the 43rd power? I would take 43 and divide it by 4. That would be 10 remainder 3. So that means I would go through 10 cycles of the pattern, then I'd have 3 left over. 1, 2, 3. So that would equal I to the third power, which is equal to negative I. And that's how you can find I to almost any power, except how much is I to the 0 power?
0. 1.
One of those answers is right. Alright, quick review on exponents. Forget about I for a minute. 3 cubed is 3 times 3 times 3, which is 27. 3 squared is 3 times 3, which is 9. 3 to the first power is 3, which is 3. What's happening to my exponents? They're going down by 1, right? So the next one in the pattern has to be 3 to the 0. What's happening to these answers? Are they being divided by 3? So the pattern has to continue, right? I mean, that's what patterns do. So what's 3 divided by 3? 1. I could do this with any base. I just like 3. So any number to the 0 power equals 1. So I to the 0 power also equals 1.